If I have an object of mass m moving with a velocity v, and I apply the force that is perpendicular to my velocity, then I will create a circular path of radius r. The direction of this force is towards the center of the path, and we call this the centripetal force. Now, of course, according to Newton's second law, there will be an acceleration having the same direction of the centripetal force, which is toward the center as well. This acceleration is generated because of the change of the velocity's direction due to the force applied. Now we know that the centripetal force is equal to MAC, where AC is equal to v square, which is the velocity of the object, over the radius of the path, which means that our FC equals the mass of the moving object times the velocity square over the radius of the path. Now, if I plotted FC in the y-axis and velocity square in the x-axis, I'd expect to get a straight line. The slope of this straight line equals m over r.
Hi students, today we are going to do circular motion experiment. For this circular motion experiment, I have a setup. This is a setup that we are going to do the circular motion. And here you can see that, this mass is attached to the string, and when I rotate this, you can see that the string tension is increasing. You see the string tension is increasing, and you look at this setup here. This is the mass which is attached to this force sensor. While I rotate this, you can see that the force sensor can provide us its force developed here due to the string, and while it rotates, this setup can provide me its velocity. From this setup, I can study the circular motion. To study the circular motion, today we have this setup. Look here, in this setup, this is the mass of the holder, and the mass of the holder is 50 gram. And today I'm going to keep two separate masses of 100 grams. So now if I place this 100 gram here, it will be 150, and here I am going to keep one more 100, so it will be total 250 gram mass in the circular motion apparatus. And here you can see, besides to that, I just kept another mass holder and with the 200 grams, to balance this to provide a uniform circular motion. Now what is my plan? I'm going to rotate it to a higher velocity, and while I keep it to a higher velocity, you can see that the force here, while I am moving it faster and faster, the force here in the sensor is increasing. And now you look here, if I leave it for some time, what will happen? The force developed in the sensor is decreasing, and the velocity is also decreasing. Now the computer can provide us a set of V and set of F. Then we have an option to convert that V into V square. Thus we can get a plot of F versus V square graph. And as per the relation, F is equal to mv square over r. Here I change the V. While I am rotating it faster and faster, its velocity is changing. At the same time, the force is changing. The computer is going to give us the plot of F versus V square. Here, the m and the radius I kept constant, right? Because while I am rotating it, its radius is not changing. Its radius is 10 centimeter and its mass is not changing. It is 250. So, being m and r constant, when we plot F versus V square graph, we will get a straight line, and slope of the graph represents m over r. Here I know m, the mass that I kept constant, I know it is 250 gram, and the radius that I kept, it is 10 centimeters. So that means the predicted slope will be definitely m over r. I mean, I can calculate it, right? The calculated value is definitely equal to the slope that the graph gives us. If these two are equal, means we can say we verify the relation for circular motion. F is equal to mv square over r. This is the experimental part we are going to do, and we are going to verify it. I'm going to do the experiment. You look here. What did I say before? It is at 10 centimeter, right? Now I am rotating it. While I am rotating, you can see this force sensor value is going to change. You look here, the force sensor value here, it is 0.5, 1, 2, and while I am rotating faster and faster, the force in the sensor is increasing and increasing. Now it reached to a value of 10 Newton. At this moment, I am going to collect the data. While I am collecting the data, the computer is going to plot the F versus V square graph. And look at this shape of the graph. While it is, I can stop it when it comes to a smaller value. Now I stop it. And as I expected, the force versus V square graph is a straight line. That means the relation F is proportional to V square, and we know that F is equal to M over R times V square, right? So the slope represents what? M over R. And theoretically, I can calculate the slope. Since the mass is 0.250 kilogram and the radius is 0.10, because it is in kilogram and in meter, so I will get the slope, and definitely this slope will be equal to the slope of this line. I'm going to get the slope of this line by doing a line fit. Okay, I'm getting 2.571. Definitely these two will be equal. If these two are equal, means we verify this relation. Am I right? Now we will do it for the another radius. That means I am going to do the second part of the experiment by changing the radius. That means I will increase the radius from 10 to 12. If I increase the radius, what will happen? If I increase the radius, what will happen? I'm going to change this radius into 12 centimeter. Let me show you. I'm going to change this into 12 centimeter. Right now it is in 12 centimeter, and if I rotate it, definitely the computer can give me another V versus F versus V square graph, and there we will get another slope. But my question is this: if I change the radius, what will happen to the slope? Since the slope is M over R, I don't even change the mass, I only change the radius. What will be the effect of changing radius? The slope will increase or decrease? Yes, it will decrease since R is more, right? So that is our second part. I will show you the video now here, or I will share you the file.